We hear all the time about the mind-blowing GPUs and the incredible AI models that are changing our world. But what about the unsung hero, the hidden infrastructure that actually makes it all possible? Well, that's what we're diving into today, the world of AI networking, the absolutely critical but often overlooked backbone of modern artificial intelligence.
So let's just start with a number that should really grab your attention. According to a recent study from Cisco, only 13% of organizations believe their networks are actually ready for the insane demands of AI. 13%. That is a massive readiness gap, and it tells you right away that something fundamental is changing under the hood.
So that begs the question, right? Why is AI completely breaking our networks? Well, the simple answer is that AI workloads are a totally different kind of animal. They are way more demanding, far more intense, and more synchronized than anything we've ever built for. Our traditional infrastructure, frankly, just wasn't designed for this fight.
And the reason for all this strain is that AI has this really fascinating two-way relationship with networking. And that's the core idea for us today. It's really a tale of two different infrastructures. AI is changing how we run our networks, and at the same time, it's forcing us to completely rethink how we build them from the ground up. Okay, so what is AI networking officially? Let's look at this great definition from Kentic. It's the convergence of AI and networking, sure, but the key is that it splits into two complementary ideas, and you really need to understand both of them separately to get the whole picture.
And this slide really lays it out perfectly. Think of it like two sides of the same coin. On one side, you've got AI for networking, which is all about using AI's brain power to make our networks smarter. And on the other side, you have networking for AI, which is all about building the powerful physical infrastructure, the muscle, that you need to run AI in the first place. Let's break them down.
All right, let's start with the first half of this equation, the brains of the operation. This is where we literally use the intelligence of AI to create networks that are not just automated, but truly autonomous. We're talking about networks that can actually heal themselves, often before a human engineer even knows there's a problem.
And the way this works is through something called the closed-loop automation cycle. The best way to think about it is like a virtual network engineer that never ever sleeps. First, the AI detects an anomaly. Then it analyzes the root cause from just mountains of complex data. It automatically triggers a fix, and then, this is the crucial part, it learns from that experience so it gets smarter and better over time. And this isn't just about automated fixes. This is about making network management radically more accessible. I mean, look at this quote from Kentic. With large language models, an engineer can literally just ask a question in plain English like, hey, is anything wrong with the network path to Salesforce? And get a real, actionable answer. That's a total game changer.
Okay, so we've seen how AI can be the brains of the network, right? Making it smarter, more self-sufficient. Now let's flip the coin and talk about the backbone. This is the more complex and, let's be honest, way more expensive side of things. The specialized, high-performance physical hardware you need to handle these monster AI workloads.
The demands AI places on a network are just extreme. We're talking about throughput of 400 gigabits per second or even more. We're talking about latency that's measured in microseconds, and we're talking about an environment where even a tiny, tiny amount of packet loss can bring a multi-million-dollar AI training job to a grinding halt.
And to really get why these demands are so intense, we need to talk about something called elephant flows. See, AI training involves thousands of GPUs all chattering with each other, exchanging these huge streams of data, all in perfect lockstep. It's like a symphony orchestra. If one musician, or in our case, one data packet, is late, the entire performance just stalls.
So how on earth do you achieve that kind of ultra-fast synchronized communication? Well, one of the key technologies is called Remote Direct Memory Access, or RDMA. What it does is it lets data completely bypass the slow parts of a computer, like the CPU and the operating system, and just move directly from the memory of one machine to another. For latency, this is an absolute game changer.
Now, for a long time, the undisputed king of this high-performance world was a technology called InfiniBand. But AI-ready Ethernet is catching up, and it's catching up fast. You've got standards like ROSI, that's just RDMA over Converged Ethernet, and industry groups like the Ultra Ethernet Consortium, all working to bring good old Ethernet up to AI speed.
So what happens when you combine the brains of an AI-run network with the powerful backbone of AI-ready hardware? Well, you get what the industry is now calling an AI factory. This is where that intelligence and that heavy-duty infrastructure finally meet, and it's driving a massive, massive shift in the market.
And just how massive is that shift? Well, how about a market this big? We're talking over $70 billion. That's the kind of money companies like Cisco and NVIDIA are pouring into building out this next generation of networking to power the whole AI revolution.
But here's the thing, it's not a one-size-fits-all market. Not at all. Different customers have very different needs. You've got the giant hyperscalers, your Googles and Metas, they want full customization. Then you have the growing neoclouds that need agility. And then you have your everyday enterprises, who often just want a validated turnkey solution they can deploy quickly and reliably.
But for all of these different players, there is one metric that rules them all: job completion time, or JCT. It's simple. How long does it take to finish an AI training run? And here's the absolute kicker. In these huge deployments, it's estimated that over 50% of that time can be spent just waiting on the network. Think about the economic impact of that, the sheer inefficiency at that scale.
Okay, so we've built the brains, we've built the backbone, we've created these incredibly powerful AI factories. So what's next? Well, the future is about AIs talking to other AIs over this incredible new infrastructure. We're moving towards a world with a whole network of specialized AI agents that can collaborate to solve incredibly complex problems.
But for that to happen, they need a new set of languages, or protocols, to communicate. And they're starting to emerge. You've got MCP from Anthropic, which is for connecting AIs to tools and data. You have A2A from Google for connecting AIs to each other across different platforms. And you've got ACP from IBM for coordinating agents locally even when they're offline. Each one is solving a different piece of this giant communication puzzle.
And this all leads us to our final and maybe the most important question of all. We are building the physical and the digital infrastructure for a completely new era of intelligence. As we build these planet-scale intelligent networks, you have to ask yourself, when AIs can finally communicate seamlessly with each other, what new worlds will they build?